started. We can see your slide. Yeah, looks fine.
Right. Yeah. Okay. So welcome to the second session of the day, and I'll be talking about cache coherency protocols. Already in the previous lecture, you've learned multi-core architectures and shared memory, multi-core multiprocessor systems. So we'll see what is a cache coherency problem and how do we deal with that. Right. So this multi-core, when you consider these multi-core systems where anyway, because for the performance reasons and to handle the memory wall problem, we are going to have multiple levels of caches between processor and main memory. And so once you have this multi levels of caches where some levels of caches are private to each of the core and some are shared by all the cores and so on. In this particular case, you can see here I've just considered a two-level cache hierarchy where level 1 is a private cache to each of the cores and level 2 cache is shared across all 4 cores. Okay, so now what is going to happen here is, so let us say if core 1 requests some data, any application running on core 1 requests some data, then it first search in the private cache. If it is not there, then it will go to the shared cache. If it is not there, it will go to the main memory and so on. But once it gets the data, it is going to be put into the shared cache and then to the private cache. So in this particular case, let us say a block is requested by an application running on core 1, which is brought into its private cache from the shared cache. And after some time, core 2 application running on core 2 requests some other data that also brought into its private cache, and core 3 also requested the same data, and unfortunately the same data requested by the application running on core 1. So the block is now replicated in private cache of core 3, and similarly core 4 also requests some data. So we know that once we have these caches, obviously you don't have to go the main memory as long as if the data is available in the caches, and that is going to reduce your average memory access time. And once it reduces average memory access time, the overall performance is going to be improved. And also another thing is, once you keep the data in private caches, each of these cores can directly work on its private caches. So multiple cores can simultaneously work, and that is going to actually improve your parallelism also, and which in turn is going to improve the overall performance. But the problem is, because of these private caches, some data may be replicated. The same data may be replicated in private caches. And now that can lead to a problem known as a cache coherency problem. Because the data, if an application updating a copy of data in its private cache, and if this update is not reflected in the other private caches where the replica of this particular data is available, then the data is going to be in incoherent state. So two different caches have the same data, but because after one is modifying that, so the data is now going to be in different caches and so on. That leads to a cache coherency problem. So I'll explain that with an example here. Just let me know if I put it in a presentation mode, is it working? Is this fine?
Yes, sir.
Right. So let us say we have a data and an address location U, and which has a value 5 in the shared cache. And now core 1 requests the data, and the copy is brought into its private cache, and that we denote as event 1. And let me know if the changes also happening in the slide, because last week when I presented, so there was some issue with this animations and so on. So now core 4, an application running on core 4 requests the same data, so the data is brought into the core 4's private cache, that is an event 2. And now core 4 wants to update the data. So previously 5 is there in the address location U, now it wants to update that to 7. After this, let us say if core 1 wants to read the data, the same data, what is the value it is going to get? Is it going to get the value 5 or 7? Because when core 1 sends a request, the request is searched in the private cache, and private cache has a copy U 5. So automatically core 1 thinks that the data is already available and then it is going to supply the data. But this event 4 is supposed to happen after event 3, and event 3 is supposed to update the value. So now core 1 is actually reading a stale copy of it. And this is called as a cache coherence problem, because the same copy is there in two different caches, but one updated, the update is not reflected in the other ones. Now let us say we consider another scenario. For example, core 2 wants to read the data and the data is not there in its private cache. So obviously it is going to go to the second shared cache. Once it goes to the shared cache, then again, it is going to read the old data, because whatever core 4 is updating, that is not reflected in the shared cache also. So now for event 4 and event 5, these cores are going to get a stale copy of it. And that problem is called as a cache coherency problem. And we need to address this. Okay, so each core will see a different value after event 3, because data is not modified in their private caches, or if the private cache is not having the data when it goes to the shared cache, there also data is not modified. And now we know that the caches are of two types, right? One is a write through cache, the other one is a write back cache. All of you know, I think, the write through and write back caches, right? So in the write through cache, whenever we update something in the private cache, we are going to update in the next level also. So now in this case, if you see core 2, if it is a write through caches, now what is the value core 2 is going to get for event 5? Because when core 4 is updating the value 7 into its private cache, because it's a write through, so core 4 is also going to update in the shared cache. So when core 2 requests the data, it finds a miss in its private cache, but when it goes to the shared cache, it's going to get the correct data. So it means write through caches solve the problem for the scenario where core 2 is reading the data and the data is not there in private cache. But still, even if it is a write through cache, core 1 is still going to read a stale copy, because write through always says if you write it to L1, then it is going to be updated in the L2. But it is not saying anything about updating in the private L1s of the other cores. So that means core 1 still has the stale copy, and event 4 is still going to read the old copy only. That means the write through caches are not going to solve this cache coherency problem. Let us say we consider the other scenario, write back. So write back again, the same thing, right? So here, I think there is a typo here. It's a write back caches where core 1 and core 2 read a stale copy. Because when it is a write back cache, core 4 update is only seen at the private cache of core 4. It is not going to be reflected in the shared cache. And as a result, when there is a request from core 1 or core 2, they are going to read the stale copies. So that means whether it is a write through cache or a write back cache, this cache coherency problem is there. How do we resolve this? What can be done to ensure that the correct copy of data is available if the copy is replicated, and everyone is going to get the correct, everyone is going to see the correct data? What is that we can do? So we need to enforce coherence. So there are two ways in which we can do. One is the write invalidation based protocol. The other one is write update based. So when I say write invalidation, whenever I'm going to write to the private cache, I'm going to send a signal to all other private caches saying that I'm going to update data in this particular address location. If any of you have the data, you better invalidate. So it effectively, the writer is going to ensure that the other processors are invalidating their copies, so that the writer is going to get the exclusive permission on that particular block to perform a write operation. And in the second one, write update, where whenever I'm going to write it, I'm going to send the data across the network, so that the bus in this particular case, so that the other caches are going to update their copies if they have a replica of this particular block. That means after the write operation, everyone will be in sync. So that means the two scenarios. One is if you have multiple copies, invalidate all other copies except the one which is there in the writer's private cache. And the second scenario is if you are going to write it everywhere, so that everything is synced. These are the two ways in which we can enforce the coherence. Now, if you see the entire design space of cache coherency protocols, it will be something like this. We'll have, if our multi-core system consisting of maybe 2 to 8 cores, all these cores can be connected by a common bus. So that is called as a bus-based shared memory system. Or it can be like a large core system, which is a many-core system, where the memory is distributed across the network and so on, and that is called as a distributed shared memory system. So that means my underlying system can be a bus-based shared memory system or a distributed shared memory system, and the caches can be a write-through cache or a write-back cache, and the protocol can be a write invalidation based protocol or write update based. So basically, if you see now, there are total of 8 possibilities for the cache coherency protocols. Bus-based system with a write-through cache and invalidation-based protocol, or bus-based shared memory system with a write-through and an update-based protocol, or bus-based shared memory system with a write-back and invalidation-based protocol, and so on. So 8 different the cache coherency protocols are there. If you consider any protocol that belongs to one of these 8 classes. Okay, so as part of this today's lecture, we'll be mainly focusing on bus-based systems, and we'll focus on the write-back caches, and then we'll look at invalidation-based and update-based. And
I don't think we are able to hear you, Dr. Madhu.
hello.
Yeah, now we can hear you.
I think there is, because I am presenting from a different room and there is some issue with the network.
Okay, yeah, now it's fine. Oh, but slides. Yeah, I think
Yeah,
it's fine.
I'll just present. Yes. Okay. So I was talking about this, the design space of cache coherency protocols, which are like basically 8 different classes. It can be based on bus-based systems or distributed-based systems, and write-through, write-back, invalidation, update-based. But so why we are considering only write invalidation or write update? Why can't we have something with read? Because these protocols are typically, whenever we perform a write operation, the data is going to be modified. But for a read operation, there is no data modification. So as a result, we don't have to worry about that. And that's the reason why here protocols are basically write invalidation or write update. Now, any protocol we design for bus-based shared memory system, which is typically called as a Snoop-based cache coherency protocol. And if you are designing a protocol for distributed shared memory system, which is called as a directory-based cache coherency protocol. And the moment we are dealing with the multi-core systems with a shared memory, so we are going to have a coherency protocol, because typically if you consider any multi-core system, caches are going to be there. And once you have caches with a private in nature, so automatically data is going to be replicated and data inconsistency or incoherency will be there. To deal with that, you need to have coherency protocol. So again, now we'll consider one of these out of these 8 classes. Let us consider one particular thing, the write-through caches we'll consider, and bus-based system, and we'll see what is going to happen here with this example. So write-through caches with invalidation-based protocol, and the cores are connected by a common bus. Now, if you see here, private caches are there and the shared cache and main memory. And after event 2, data is replicated in private cache of core 1 and private cache of core 4. Now core 4 is going to perform a write operation. trying to update the value 5 to 7, because it's a write-through cache, it is also going to update in the shared cache. So that means the shared cache copy is also going to be updated. And it's an invalidation-based protocol. So core 4 is going to, before writing, it is going to send an invalidation signal on the bus so that all the cores are going to look at all the cache controls of the private caches, are going to snoop on the bus and then take that address and search in their caches. And if they find any copy, they are going to invalidate. So like that, core 1 controller, L1 controller, when it sees that address, it checks in the tags and it found an entry and it is going to invalidate that copy. But whereas core 2 and core 3, they could not find any data, so they are not updating anything. That means after event 4, core 1's copy is invalidated, shared cache copy is updated, and the core 4 copy is also updated. Now if you see event 4, when core 1 wants to read it, it finds a miss in the private cache, then it is going to read the data from the shared cache. So it is going to get the correct copy. Similarly, if core 2 is going to send a request, it anyway finds a miss in the private cache. It's not there earlier. So it is going to still read the data from the shared cache, and which is also going to get the value 7. This you can clearly see now with the simple this write through and invalidation based. Now we overcome the problem of incoherency across multiple caches, and everyone is going to get the correct copy of data. So this is the basic idea of cache coherency protocols. And now we'll discuss how this cache coherency protocol is going to be implemented. Of course, we are considering write back caches with invalidation based and an update based. We'll see that how we are going to implement different type of protocols and what are the protocols that are implemented in current Intel based systems or AMD based systems and so on. So I'll just explain that step by step. So if I want to implement, let us consider a bus based system. That means you can see here core 1, core 2, core 3, core 4 all have their private caches, and all these private caches are connected by a common bus. On the other side of the bus, you have shared cache, right? And because it's a bus-based system, any cache coherency protocol we design for bus-based system is called as a snoop-based cache coherency protocol, because the cache controllers are going to snoop on the bus and take that address and then search in their private caches. That's the reason it's called as snoop-based. And to implement any coherency protocol, what we need is we need to maintain the state information for each of the blocks present in the private caches. For example, if the private cache has 1024 blocks, now we are going to have 1024 states. Each block will be in one state. And that state can be an n-bit coherency state. It can be 2-bit, 1-bit, 3-bit, or whatever, depending on what is the protocol we are going to design. And that state is going to specify in which state that particular block is present. Whether the block is invalid, whether the block is modified or shared, different things are there according to the protocol. Right? And every time whenever any core wants to perform a write operation or a read operation or whatever, it is going to place a cache transaction on the bus. And all the private caches controllers are going to snoop on the bus, and then they'll check in their caches. If they find the data, they'll take an appropriate action depending on the state transitions. All these state transitions are given by a state transition diagram. In other words, a cache coherency protocol is defined as a state transition diagram. We'll see how the state transition diagram look like for different type of protocols in the next slide. So coherent state for each block location will be there. It's a one-to-one mapping. If you have 512 blocks, then you have 512 n-bit states, one for each of the blocks. And cache controller or coherence controller is going to update the state of the cache block in response to processor and the snoop event. Whenever processor is going to perform a read operation, if nowhere the data is going to be there, the block is right now in the invalid state, is going to get the data from this next level, and maybe it will put the block in the shared state. If it is an MSI protocol or if it is an MESI protocol, it can keep the block in the E state, and different states are there. And similarly, for example, core 1 has the data in a shared state and core 4 wants to update that particular copy or wants to write to that particular copy. Now, core 1 has to invalidate their copy so that the copy will go to core 4 and core 4 is going to perform operations. At the end of this operation, core 1's copy is going to be an invalid state and core 4 copy is going to be a modified state and so on. So different type of state transitions are going to be there. And the controller updates the bus transaction also. Depending on the cache coherency cache transaction, the bus transaction also going to be placed by individual controllers and so on. We'll see all those things in the coming from the next slide. Okay. So we'll start with the a simple three-state protocol MSI. M stands for modify, S stands for shared, I stands for invalid. And this is a write-back invalidation based protocol. That means when you have two levels of caches, and whatever you write at the L1 level, that will not be reflected to the next level. And it will be reflected to the next level only when you evict the block from L1. That is what is called as the write-back caches. And it's an invalidation based protocol. So that means whenever I want to perform a write operation, I'm going to send an invalidation signal to others. Others are going to invalidate their copy, and I am the only one having exclusive permission on that particular block to perform a write operation. Right? And here we use some nomenclature. Here, PR read is a processor read. Similarly, PR write is a processor write. And there is a bus read signal, bus readx signal, which is required typically when I want to perform a write operation. I need to get the exclusive permission on that particular block. That is the reason why we consider bus readx. And any transaction initiated by processor, we are going to put it in a this bold line. And if it is a bus snooper initiated transaction, we are going to put it in dotted lines. Now we'll see. Let us assume that initially nothing is there in the cache. Once nothing is there or the block is not there, we consider the state of the block is invalid. And then let us say processor core 1 initiates a read request saying that it wants to read a block of data and it could not find the data in its private cache. So that means the state of the block at present is I indicate the block is not present. And then it wants to read the data. So when it is going to read the data, and once it gets the block of data from shared cache or other caches or something, now it is going to keep the block in the shared state. That means there is a transition from I to S on processor read. You can see here I to S, there is a processor read transaction and there is a bus read transaction, which is nothing but the semantics of this is from one state to another state, there is a state transition. And that happens when there is a processor generated operation, which is processor read. And for that, there is a bus read transaction placed by the bus snooper. Right. So here you can see this is basically core 1, which wants to read the data. It is going to place a bus read signal on the bus and it places the block in the state. And any core which sees the data, which sees the transaction as bus read, then it can try to supply the data. Generally, we consider here only if the other core has the data in a modified state, it can supply. If that is not the case, the lower level cache, there is a shared cache, is going to supply the data when it sees a bus read transaction.
Sir,
so yeah.
Sorry to interrupt. Actually, your slides are lagging. I mean, we are still on the previous slide of Snood-based coherence protocol implementation.
Snoop based. Okay, I think there is a problem with my presentation. Now, maybe what I'll do is I'll just stop this animation part. This is fine, right? You can see the
Yes.
MSI write based protocol.
Yes, sir. Yes, sir.
Right. I think this is fine. I'll just go ahead with this. Okay. So now let us say initially the block is not there in a private cache of core 1, but core 1 wants to read it because application running on core 1 initiated a load transaction and it has to get the block of data. What it does is once there is a load request, there is a processor read request, it is going to the core 1 cache controller or the coherence controller is going to place a bus read signal indicating that particular address, saying that I need the data for this particular address location, and that is the transaction that is placed on the bus. And now this transaction will be seen by all because this is a Snoop based protocol. All the cache controllers are going to snoop on the bus. They'll see that, okay, there is a read request from someone with this particular address, and everyone is going to search in their caches to see whether they have the data in a modified state or not. If any of them have the data in a modified state, that particular core is going to respond to that. If no one has the data in a modified state, then automatically the lower level cache, that means L2 controller going to see this transaction and it is going to place the data. Once the data is placed, core 1, which requested this data, it captures this data and put that in that particular location that is determined by your cache coherency, your cache replacement policy. And in that it is going to put the data and change the state from I to S. So there is a state transition from I to S on processor read, and it is placing a bus transaction, which is called as a bus read. But for example, if core 1, instead of read operation, it wants to perform a write operation. Now what it does is, it is going to place a processor write transaction, and processor write indicates that no one else should have the copy after this core is going to perform a write operation. And that's the reason why it is going to place a bus read X signal. There is a difference between bus read and bus read X. Bus read means other cores can have the data. They can keep the data as it is. But bus read X means if the other cores have the data in a shared state or whatever, or even modify, they have to just invalidate, and so that the requester is going to have exclusive permission. Bus read exclusive. That is what the semantics of that bus read X. And when there is a processor write operation, the end state of this block is going to be from I to M. So if you see processor read I to S transaction, but whereas for write I to M is there. And now, so once let us say core 1 perform a read operation and it initiate a bus read signal, and let us say core 2 has the data in a modified state. What could be the state of that particular block in core 2 after core 1 initiated a read transaction? Any idea? The scenario is core 1 is not having the data, but core 2 has the data in a modified state, and core 1 wants to read it. What could be the state of core 2 block? So in other words, let us say I want the data and you have the data in a modified state. Obviously, when you say you have the data and modify, then you are the only one having the data. Even the LLC also will not have the correct data. So you have to supply the data to me. Once you supply the data to me, we both have the same data. Then what should be the state of your block?
Shared.
Shared. Because only the shared a block can be there in shared state in multiple caches. But if the block is there in a modified state, only one core will have the data in a modified state. You cannot have more than one cache having the same data in modified state. Modify means only one core private cache is going to have, and a shared means multiple cores can have the data. So because you have the data in a modify and I wanted the data for a read operation, so you are going to supply the data to me and you change the state from modify to shared. That is what is reflected here in the dotted lines from M to S on a bus read signal, and there is a flush is there. Flush indicates that this block which is there in a modified state, that is going to be flushed on the bus so that the core which is requested the data is going to get that. But there may be another core, let us say another scenario. For example, core 2, core 3 have the data in a shared state, and core 1 wants the data for a read operation. In that case, core 2, core 3 are not going to supply the data. They can just keep the data in the shared state, and LLC is going to, or last level cache or L2 cache is going to supply the data to core 1. In that case, you can see here, there is a bus read signal and it will be there in the same state. So there is a self loop on S state with a bus read without supplying the data and so on. Right? And you can see the other scenario. For example, core 2 is having the data in a shared state and wants to perform a write operation. What is going to happen to core 2's copy when core 1 is going to perform a write operation? And note that this cache coherency protocols, if you want to understand, then always you have to consider scenarios, different scenarios, and then see what is actually happening and so on. Otherwise, if you just look at the state transition diagram, you will not get anything. So now the second scenario is core 2 has the data in a shared state, but core 1 wants to perform a write operation. What will be the state of core 2's block? Because when I say write operation, only one core should have the data. Even if the other cores have the data, they have to invalidate their copy. So that means core 1 is going to place a processor write. For that, it is going to initiate a bus readx signal. The moment any other core sees a bus readx signal, then automatically they are going to invalidate their copy. That is what reflected here. For example, there is a dotted arc from S to I on processor readx. That means the core 2 is going to invalidate its copy. And then the core 1 is going to have the copy in an exclusive state, in a modified state. Because I'm going from I to modify, and if anyone else has the data in a shared state, they are going to invalidate their copy. That is what is reflected here. Right? So we already saw from modify to shared on a bus read signal. Similarly, shared to invalidate on a bus readx signal, and I to S on a processor read, and similarly I to M on a processor write. Right? And now let us say I have the data in a shared state and I want to perform multiple read operations. Do I have to inform anyone? If I'm going to perform multiple reads from my block, I have a block of data and I'm keep on reading the data. I don't have to inform anyone because I have the data in a shared state. I'll just keep reading the data any number of times without informing anyone. That means without placing any bus transaction. That is what is reflected here. There is a self loop on S state for processor read without placing any bus transaction. That is represented by the dashed line. And similarly, if I have the data in a modified state, I don't have to inform anyone. I can perform any number of reads and writes without placing any transaction. That is what is given on there is a self loop on M state at the top, processor read without any bus transaction, and similarly processor write without any bus transaction. Is it clear? And if you see, this is basically a simple 3-state cache coherency protocol. This ensures that the data is going to be coherent across multiple private caches. Okay, I'll ask you one simple question here. Maybe someone can answer. Let us say core 2 has the data in a modified state and core 1 wants to write to that particular block. What is the sequence of steps happen? And where do you think core 1 is going to get the data?
So can you repeat the question?
The question is core 2 has the data in a modified state and core 1 wants to perform a write operation to that particular block. What is going to happen? Who is going to supply the data to core 1? Is it shared cache or core 2?
Core 2.
Core 2 has to supply because core 2 has the data in modified state, then core 2 has to supply. Okay, core 2 has supplied the data to core 1, but what happens to the state of core 2's block?
Become shared.
Shared? Because I said like core 1 wants to write.
Yeah, it becomes invalidated.
Invalidated,
Because
right?
cache 1 should write. Yeah.
Yes,
Like core 1
because
should
cache
write.
1 wants to write it, so automatically your core 2 private cache has to invalidate that copy. That is what is given here. For example, you can see there is a dotted arc from M to I on bus readx signal. And that is because core 1 initiated a processor write request with a bus readx. Core 1 places a bus readx signal on the bus and core 2 sees that particular thing, and because it has a copy in M state, it is going to supply the data by using a flash, and then it is going from M to I. So that is what is given. Okay, so this is basically because I know that at the end of write operation only one should have the data, the others have to invalidate. And similarly, if you are going to replace the block, because you also have cache replacement policies and a block may be selected as a victim. And what do you do on a write back caches when there is a block evicted by a cache replacement policy? Whether cache replacement policies are discussed in one of the previous classes. Huh? No answer?
Yes.
Yes. So when there is a block evicted by a replacement policy, what is that we are going to do in the case of write back caches? Are we going to write it to the next level or not?
No, we write into the buffers.
No, fine, but from the buffer to the next level, but at least like, right, are we writing to the buffer or not? Or is it necessary to write to the buffer always when the replacement policy selects a victim block? What is the advantage of write back caches over write through?
It won't immediately be written into memory and it will be like.
So basically you are saving on memory bandwidth. You don't have to keep on writing to the next level. You accumulate all the writes in the L1, and when you are evicting the block, you write once to the next level. That is the base advantage of write back. But now when the replacement policy selects a victim block, it is going to see whether the victim block is dirty or not. There is a separate bit associated with each block, and if the bit is set, that means when I perform a write operation, I'm going to set the dirty bit 1. If the dirty bit is 1 at the time of replacement, when I select that particular block as a victim, if the dirty bit is set, I'm going to write it to the next level. Otherwise, I'm not going to write it to the next level. That is also seen here if you closely observe this state transition diagram. For example, you can see from M to I on replace. Replace is effectively your replacement policy selected this particular block as a victim. In that case, we are going to have a bus write back. But whereas if there is a shared state to I, when you are replacing, you are not writing back, because shared state means the block is clean. You don't have to write it back even when it is selected as a victim. But in the case of modify, the block is already modified. When the replacement policy selected this block as a victim, you have to write it back. So those are the two transactions given here. M to I transition on replacement with a write back, and S to I, there is a transition on replacement but without any write back. Is it clear? So this is about the MSI 3-state invalidation based protocol. Always remember, if there is a write operation, we'll be going to the modified state, whether it is from the shared state or an invalid state. Ultimately, we are going to modify state for a write operation. And if it is a read operation, we'll be just going to shared state. And if it is already shared state, we'll be in the same shared state as it is. So the end state for a read operation is a shared, end state for write operation is a modified. Okay. So now, if you see here, there is some issue with this MSI protocol. The issue is, let us say my application, ultimately it wants to update some location in a block, but first it wants to check some condition. That means it wants to read the data, check some condition, then it wants to update. So in such cases, if you use MSI protocol, it is not efficient, because what is happening in MSI is, when you are first reading, you first put the block in the shared state by placing a bus read signal on the bus. Next, when you want to write it, you go from S to M by placing bus read X signal. So basically, you are going to place two transactions on the bus. First bus read signal, the next is bus read X signal. But anyway, you know that you are the one ultimately going to write to that particular block. Why can't you minimize these bus transactions? First of all, why do we have to reduce the bus transactions? Is there any problem with the bus transactions? If you have more bus transactions, what is the problem we are going to face? Any idea? Remember, this cache coherency protocol itself is an overhead to the multi-core system. We require this to ensure that the data is coherent. But to ensure the coherence, we are going to have all these extra transactions and so on, which actually eats away the memory bandwidth. While we are using the bus, so the other cores may not be using the bus for useful operations and so on. So your overall efficiency of the multi-core system is going to be degraded if you are going to use this coherency protocols. But of course, correctness is the important thing, first and foremost thing. Then only the performance is going to come in, right? So that's the reason why even if there is an overhead, they have to use this coherency protocol. But now the thing is, when you have to use a coherency protocol, why can't we optimize the coherency protocol? Try to reduce unnecessary transactions on the bus, so that the bus will be utilized efficiently for useful operations. And that is where like there is a drawback with MSI, because if I know that I'm going to first read and then write, no one else is going to have the copy of it. Why can't I reduce the number of transactions placed on the bus to a single one? So with this idea, they came up with a modification to this MSI protocol, and that is MESI protocol. So here we are adding an extra state to MSI protocol, MSI plus exclusive E state we are adding. This E state is going to differentiate between a block which is going to be writable versus the block which is written. If it is a written, means already it is a modified state. Going to be writable, indicating that it is an exclusive state. And when the block is in exclusive state, the next level cache is still have the same data as that of the exclusive block. Both have the same data. Only thing is, once you are in exclusive state, next time if you want to perform a write operation, you don't have to send any transaction on the bus saying that I'm going to perform this, that, and so on, because you are the only one having the exclusive copy. Then you can move from E to M and perform your write operation. So that as a result, you are now reducing the number of transactions from 2 to 1. Previously, we were having bus read and bus read X. Now we are going to have only one. That is the main advantage with this MESI. So we have ISM, same as MSI protocol previously, and we have another one E, which is an exclusive copy. So it means whenever we are moving from I to E or S, we need to have a mechanism. How do we determine whether we have to put the block in an S state or E state on processor read? Because initially core 1 wants to read the data is not there in its private cache, so the block is an I state. Now we have to bring the data, but when we are bringing the data, in which state this particular block is going to be placed? Is it S state or E state? We put it in E state if no one else has that copy of data, no other private cache has the data, then we're going to straight away put this in E state. If any of the other caches have the data, then automatically we have to put this in S state. So how do we determine that? So for that, we are going to have one extra, a simple mechanism. We are going to have a shared wired R signal, which is shared across multiple cores, multiple private caches. And every time whenever we are going to place a bus read signal on the bus, everyone, because the cache coherence controllers of all these private caches are going to see that, snoop on the bus, they search in their private caches. If they find the data, then they are just going to set this wired R signal by 1. Once the wired R signal is set to be 1, I know that someone else already have the data, so I have to keep the block in S state only. If no one else accepted this wired R signal, indicating that the block is not present in any of the private caches, so I can safely put the block in E state. So that is the basic idea of this MESI, and this is a hardware implementation where all we need is one extra bit line, and that is going to be a wide R mechanism. If any one is updated, then automatically, because a wide R is effectively, if any of the inputs is 1, output is 1. With that idea, we can implement MESI protocol. Okay, so all we need is, like, when we are going to bring the block for a read operation, we just search, we just check wide R signal whether it is 1 or 0. If it is 1, put the block in S state. If the wide R signal is 0, we put the block in E state. Now if we see the state transition diagram for this, I just put for the comparison purpose. We already saw MSI protocol, and now we are designing MESI protocol. So I place these two back to back, adjacent to each other, so that you can clearly see what is the difference, right? So I to S. Previously in an MSI protocol on a processor read, we are going from I to S. But in the case of MESI, on a processor read, based on the shared line, shared wired R line, if the shared wired R line is 0, we are just going from I to E. If the shared wired R line is 1, we are just going from I to S. That is what is given by S bar and S in both the cases. And for a processor write operation, it's the same as that of MSI protocol. There is no change. Similarly, S to M, there is no change. But now, if the block is there in E state, and processor wants to perform a write operation to that particular block, You can see here E to M for a processor write without placing any bus transaction. This is the main advantage with over MSI. You see in the MSI, I to S bus read, S to M bus read X. But whereas in the case of MESI, I to E bus read and E to M, there is no transaction. We cut down this extra transaction on the bus, and that is actually saving us the bandwidth, and that bandwidth we can use, or the bus availability is increased for performing any other useful operations. And the remaining things are straightforward. So this is the main difference between MSI and MESI. We just reduce the transaction from E to M because E itself is indicating an exclusive, so you can just perform without intimating anyone else. And the rest of the things are E to I, E to S, all these are straightforward. Can you tell me when are we moving from E to S? What is the condition on which we will be moving from E to S?
When some other core has the same data.
So let us say core 1 has the data in an E state, and now core 2 wants to read the data. When core 2 is sending a bus read signal, core 1 sees that bus read signal. The moment there is a bus read signal on the bus, and core 1 data is going to be now moved from E to S, and again it can place the data on the bus so that core 2 can get it. That is what is actually flash dash we mentioned here, which is a cache to cache transfer. So some systems are supporting cache to cache transfer, some systems are not supporting. Cache to cache transfer is like a private cache to another private cache transfer. So now core 1 is sending the data and changing the state from E to S, and core 2 is also going to get the data in the S state, and the resultant state in core 2 also is going to be S because core 1 is already having the data. And other than that, the remaining things are straightforward. Okay, so this is about MESI. Just a slight modification to MSI to cut down unnecessary transactions on the bus. By the way, remember, so if you are going for more and more states, we can cut down unnecessary transactions on the bus. So the bus can be utilized efficiently. But as we are increasing the number of states, the number of bits to indicate the state is going to be increased. Of course, here 3 and 4, there is no change in the number of bits to be representing the state, because here we require anyway 2-bit information, whether it is a 3 states or 4 states, up to 4 states we can just have, right? So 2-bit information will be there for each of the block state. And that is going to say whether it is a modify, exclusive, shared, or invalid. So these are the basic protocols, coherency protocols, MSI and MESI. But if you see Intel and AMD processors, they're actually not using this. They modify this and then they've used something else. And we'll discuss that now. So Intel uses MESIF forward. Okay. So why are we requiring this? I'll just give a scenario now. Let us say I have 4 cores in a multi-core system, and 3 cores have the data in a shared state. Let us say core 1, core 2, core 3 have the data in a shared state. Now core 4 wants the data. So core 4 places a transaction on the bus indicating that bus read with address. Who is going to supply the data to core 4? Is it core 1, core 2, core 3, or LLC? Who can supply the data to core 4? According to MSI or MESI?
In MESI, either of the cores can.
Hmm?
In MESI, either of the cores can.
Okay, but do we have that? For example, if you see the state transition diagram, right? If there is a if there is a cache to cache transfer, but now how do we decide whether core 1, core 2, or core 3? Because everyone is trying to place the data on the bus. Now there is a bus arbitration logic, and then someone has to win the arbitration and so on. There is another overhead. If more than one cores are there, and also again, like if there is no cache to cache transfer, so simply what is going to happen is always the LLC is going to supply the data. And but your LLC may be very far from the core, and that will increase the overall latency. So why can't we decide why can't we designate one particular core is having the capability of forwarding the data, and that is what is incorporated in MESIF. One among the sharer cores of a block will keep the block in the forward state, while all others will keep the data in the S state. And anyone has the data in F state. If someone requires the data, then this particular core is going to forward it. That means we are just electing a leader among all the sharers. And this leader is going to supply the data if anyone requests the data. That's the basic idea of MESIF. So if we consider this, the advantage is, so because now we don't need to, now the sharers need not fight among themselves saying that, okay, I'll forward and so on. Whoever has the data in F state is going to forward, and whoever is having the data in S state, they're not going to forward anything. But how do we select this leader among multiple sharers? That is also, again, they came up with a simple idea. Whoever requested the data latest, that is going to be having the data in the F state. For example, initially core 1, none of the cores have the data. Now core 1 requests the data. So core 1 is going to get the data from LLC. Now core 1 is going to place the data in F state. After some time, core 2 wants the data, same data. Now it is going to place a transaction, and core 1 is going to supply the data to core 2. And now core 2 is having the leadership now. F will be there in core 2's private cache, and core 1's copy is going to be in shared state. Now after some time, core 3 requests the data. Now core 2 is going to supply the data to core 3, and core 3 copy is going to be in F state, and core 2 copy is going to be in S state. So that means whoever is the recent reader who is going to get the block in the F state. So that as a result, like this leadership is distributed across all. Everyone is going to share this leadership uniformly. Whoever is reading recently, it is going to get the copy in the F state. And also another thing is, if you see the least free, the LRU policy, right? So least recency based replacement policies are there, right? So LRU policies, like the block which is least recently used is going to be evicted. But now if you access that block, it is going to be placed in the MRU position. Once you place in the MRU position, it is less likely that the block is going to be evicted immediately. So as a result, this F block is going to stay there for some more period. Okay, but now tell me, let us say core 1, core 2, core 3 all have the data, and core 3 is the latest reader. So the block is there in F state in core 3. And unfortunately, core 3 evicted this particular block. Now who is going to get the leadership? Core 1 or core 2 or none of them? Any idea? If we are evicting an F block from a core, we just leave that as it is. So we are not going to actually select another leader. So that next time if someone else requests the data, because you don't have any block in an F state, any core having that particular block in F state, so the LLC is going to supply the data to it. That's it. If there is a block in F state, then that particular block is going to be supplied. Otherwise, like we just leave it to the next level. And this type of protocol is implemented in Nehalem. And after that, all the Intel-based processors are actually using this MESIF protocol. Now, if you see the state transition diagram, again, I'll just put MESI, and then MESIF. And you can clearly see only the difference between those two wherever we have. Right? Initially in the MESI I2S, we are going if shared line is asserted, or I2E if shared line is not asserted. But whereas in the case of MESIF, we first go to I2F, right? You can clearly see, rather than going to S. And of course, if none of the other cores have the data, then we are going to go from I2E. I2E transition is same both in MESI and MESIF, but I2S or I2F depends on. So in the case of MESI, we'll just go from I2S if someone else is having the copy, and MESIF will go to I2F rather than I2S. And the rest of the things are similar. And again, you can see F2S transition is also there in MESIF, where someone else is performing a read operation, then you are going to supply the data to that core and you change the state from F to S. But the rest of the things are exactly same as this one. So the advantage with MESIF is, if some other core requests the data, you don't have to supply the data from the lower level cache, which is typically taking more amount of time. And if the data is there in the private caches and the private cache access latency is lesser than the shared cache, then MESIF is going to be beneficial. And that is what is happening here. And because most of the times when you are dealing with these multi-thread applications and the data may be already there in some of the private caches, why can't we supply the data from that rather than waiting for the LLC to supply? Because there may be LLC may be taking multiple cycle latency, and also it may have to come through this network on chip, which is going to take some more extra cycles and so on. It is better you supply the data from the private cache. So that's the basic idea of considering this MESIF. Okay. And when Intel implemented this MESIF with a forward state indicating that one of the sharers is going to take the leadership and supply the data to the requesters, AMD came up with a different idea. They consider owned. Rather than the leader, here there is an owner. MOESI protocol they consider. That is MESI plus owned state. And this owned state avoids the need to write modified data back to the memory before sharing it. Now, if you see here, let us say block is there in a modified state. A core 2 has the data in a modified state. Now, core 1 wants the data to be read. But what is that we are going to do? Core 2 has the data in a modified state and core 1 wants the data for a read operation. What are we going to do? Can anyone answer this? Core 2 has the data in modified state. Core 1 wants the data for a read operation. Whether core 1 is going to get the data from lower level cache or core 2?
Core 2.
Core 2 is going to supply the data. Now, when core 2 is supplying the data, after supplying, what will be the state of the block in core 2 and core 1? Because core 1 is asking for a read operation only. What will be the state?
Shared for both of them, maybe?
Oh, yeah, it's shared only. Both of them are in the shared state, right? But once the block is in a shared state, what about the contents of the lower level cache? According to our basic semantics, when the block is in a shared state, it should be same as that of the lower level cache also, right? If you see here in MSI, yeah. So in the shared, 2 or more caches have the copy and it is same as the lower level cache. Okay, but now it is same as lower level cache means when core 2 is sending the data to core 1 by using the flush command, data is placed on the bus, LLC or the lower level cache is also going to update its copy. So that means when core 2 has the data in a modified state and core 1 is requesting the data, core 2 is going to place the data on the bus. Data is updated in the lower level cache, that is L2 cache. Similarly, L1 cache of core 1 is also going to be updated. So basically what is going to happen is every time when you are going from M to S a state or M to I or whatever, it is going to be updated in the lower level cache. Now consider a simple scenario. Core 2 has the data and modify, core 1 wants the read operation. Now the data is returned to the lower level cache and data is applied to core 1. And after that, core 1 updates its copy and again core 2 is requesting the data. In that case also core 1 is supplying the data to core 2, but the data is updated in the lower level and so on. Every time when you are going from S to M this way, every time we are updating the lower level cache. Why do you have to update this? Because typically if you see producer consumer type of thing, right? Someone produces, someone is going to consume and so on. In such type of scenarios, it's actually not a good idea to update the lower level cache. Because if you are updating the lower level cache, you're going to write to the buffer or to the next level, which is unnecessarily wasting the bus bandwidth. And if you want to improve that, if you want to utilize that efficiently, we try to avoid this writing to the lower level and we write only once. And that is what is called as MOESI protocol. So the owned state avoids the need to write modified data back to the memory before sharing it. In other words, when core 2 has the data in a modified state and core 1 wants the data, what it does is core 2 cache is going to supply data directly to core 1 without updating in the LLC. But now core 2 is going to change the state from modified to owned. And only when you are evicting the block in owned state, we are going to update that in the lower level. Or if you are evicting the block in a modified state, that also we are going to write it to the lower level cache. That is already there in this particular thing. If you see, so in a modified state, when you are replacing, for example, yeah, you can I'll just go back here. Yeah, you can see if there, yeah, in MSI you can see a block modified state, and if you are replacing, you are writing back. The same logic is carried forward for MESI and MESIF also. So basically, what we are going to do is, when we are evicting a block in an owned state or a modified state, we'll be updating that to the lower level. Otherwise, we are not going to update it. So unlike MESI, a shared cache block may be dirty with respect to memory in the MOE-SI. But in the case of MESI, if the block is a shared state, the block and the lower level cache block both have the same data. But that is not true with MOE-SI. If no cache holds a cache block in the O state, automatically the lower level cache or the memory copy is up to date. And when there is a read request made to this particular block, it is the responsibility of the core that holds the block in O state to supply the data. Previously in the MSI, what we have done is like MSI or MESI, if a block is there in the shared state in multiple caches and some other core requests the data, we'll be actually supplying the data from the lower level. But here, if the block is there in one of the caches in a O state, that core is going to supply the data. And this is implemented in AMD processes starting from Opetron and so on. So basically, owned state is added to MOSI in the AMD process, and F state is added to MESI in the case of Intel processors. And now if you see the state transition diagram, again, MESI and MOSI. All I've done is that added O state. Now you can see only those changes. So I have a block in modified state and some other core requests the data in for a read operation. That core is going to place a bus read transaction. Once I see the bus read transaction on the bus and I have a block in the M state, I'm going to change from M to O. You can see the top arc, dotted arc from M to O. And so that means I'll be now keeping the block in the O state, but I'm flushing the data so that core 1 is going to get the data. Right? And if I have the data in O state, next time when I'm performing a write operation, then I need to place a bus read X signal. Can anyone tell me why this bus read X signal is required? Why there is a bus read X signal if you are going from O to M state? If you say a bold arc between O to M in the MOESI protocol, there is a bus read X signal. Can anyone tell me why bus read X signal is required on a processor write request to a block which is in O state?
Because the data is changing and then it should be reflected on the cores.
Right, but the thing is like it can be reflected on the course. Why do we have to reflect? Because it's it's not an update based protocol, it's an invalidation based protocol. Do we have to invalidate any other course copy? In other words, if I have the data in an O state, is there a possibility that the other cores have the data in a shared state?
Yes, there's a
And if I have
possibility.
the data in a modified state, is there a possibility that the other cores have the data in shared state? As I said previously, this cache coherence protocols, entire protocols are like basically you have to just come up with these scenarios and then analyze. If I have a block in modified state, is there a possibility that the other cores have the data in the shared state? Shared or exclusive or something? Yes or no?
shared if we are updating the LLC, but I think it would be in O state.
And no, I'm talking about only the other private caches. Other private caches, if I have the data in M state in my private cache, is there a possibility that the other private caches have the data in a shared or exclusive state?
No.
No, right? Because the modify indicating that only one core has the data. But owned state indicates that there may be other cores have the data, but I am the one who takes the responsibility of writing back to the lower level. So that is the reason why if you see on O state, if there is a processor write, there is a bus read signal. But on M state, if there is a processor write, there is no transaction on the bus. If you see the top two states in this MOESI protocol for a processor write, for M state, there is no bus transaction, but whereas for O state, there is a bus transaction bus readx. That is because if you have a block in O state, the other cores may have the data in their private caches in a shared state. But that is not true with modified state, right? And but otherwise, the rest of the things are exactly same as your MESA protocol. In other words, if you see, the Intel-based processors are focused on distributing this responsibility of forwarding the data to the other private caches by using F state. And in the case of AMD processors, they handle this unnecessary writes to the lower level caches by adding a new state O. So all these are, whether it is an MSI, MESI, MOSI, MESIF, all these are invalidation based protocols. But in our design space of cache coherency protocols, we also have update based protocols. We'll just discuss one update based protocol in a couple of minutes. That is called as a Dragon protocol, which is also, again, I'm using only write back caches, same as the previous ones, write back, but we are using an update based protocol. When I say update based protocol, if I'm going to update something, I'll be updating in all other replicas also. That means there is no question of invalid block. If the block is present in the cache, it will be in one of these valid states, right? And that's it. And you're not going to send any invalidation signal before you perform a write operation or whatever, because it's an update based. If you want to perform a write operation, you send the data to the others and they'll also update. And here this Dragon protocol consists 4 states. E state exclusive, same as our MESIF, whatever we can say, MESIF or MESI, MOESI. M state is also same, whatever we discussed. The semantics of E and M both are same as that of the previous protocols. But we have shared state is now considered in 2 ways, shared clean and shared modify. These are the 2 states we've considered. Shared clean is 2 or more caches have the block and the next level cache or the memory may or may not be up to date. That is what the shared clean. And the shared modify means 2 or more caches have the data, but the next level cache is not up to date. Because this is similar to modify. In the modify state, we can definitely say that the next level is not up to date. The similar way we are considering shared modify, where the next level is not up to date with the current copy, but my copy may be there in the other private caches also. That is what is a shared. Shared indicates multiple private caches can have the data. Modify indicates that the next level is not up to date. That is combined, put together into a single state SM. And similarly, shared clean means, again, so I'll have multiple copies and may not be up to date with the next level and so on. And again, here there is no invalid state because it's an update based protocol. And now what we have done is, let us say initially we initiated a read request. Processor initiated a read request, that is a load request is generated. And now, if the block is not there in the cache, you have to bring the block. When you're going to bring the block, you have 2 options. Either you keep the block in the E state or SC state, depending on whether anyone else has a copy or none of them have the copy. If none of them have a copy, you keep the block in E state. If someone has a copy, you keep the block in SC state. That is what this, if you see there are the top arrows, inward arrows to E state and SC state. And there is again S bar and S is there, similar to MESI protocol we consider, right? So depending on whether others have the data or not, we are going to put the data in E state or SC state. Now, if you want to perform a write operation to an E block, Because it's an exclusive copy, no one else has the copy. When I want to perform a write operation, I can straight away go from E to M, similar to MESA protocol, whatever we considered previously. So there is a diagonal arc from E to M on processor write request. But whereas in the case of SC shared clean, if you are going to perform a write operation, I have two options. Either I'll be going to M state or I'll be going to SM state, depending on whether someone has the data or not. If no one has the data, then I'll be going from SC to M. If someone has the data, I'll go from SC to SM. That is what is these two arcs between SC to M and SC to SM. Okay, so for a read operation, we'll have two options, either E or SC. And then on this E or SC, when we are performing a write operation, we'll be going to either M or SM state. And let us say I have a block in E state and someone else wants the data for a read operation. Then the other core is going to place bus readx signal. Then we'll be moving from E to SC. That is what the top arrow here, E to SC, which is similar to whatever we considered previously from E to S state, same as that. But if the processor initiated a write request instead of a read request, previously for a read request, we moved to E or SC. But if it is a write request, we'll be going to M or SM state, depending on whether others have the data or not. M state is like no one else has the data, then I'll directly straight away go to an M state. And if someone has the data, then I'll go to SC state. Those are like bottom inward arcs to SM and M state. And similarly, again, you can move from SM to M or M to SM depending on the transactions, whatever you're placing. But if you analyze this, you can actually understand this full picture. This is basically like an update-based protocol where no invalidation signal, and every time when we are sending any request, we are going to update in all other replicas. So at the end of this transaction, all the replicas have the same data as that of the writer, which has the data and so on. Okay. And I have, let me take maybe one more, two slides, which I'll just briefly explain, because so far whatever we consider is like when we have a limited number of cores connected by a common bus and our shared cache is a monolithic single cache and so on. But especially when you go for a many core system, shared cache is distributed across multiple cores, not necessarily going to be a monolithic one. In such cases, how do we handle the coherency protocol? And that is what we consider scalable multi-core processors, where you can see previously we were having the shared cache a monolithic connected by a common bus to all the cores. But now here the shared cache is distributed across all, right? And the private cache for each of the cores, and part of the shared cache is with each of the cores. And now how do we maintain the coherency when the shared cache is distributed across multiple things? So for that, what we've done is like the private caches, the state information is same as that of whatever we consider the bus-based systems. But for the shared cache, we are considering the state transitions by considering this extra bits, which are like presence bits and a dirty bit. If you have n cores in our system, then we are going to have n+1 bit vector for each cache block present in the shared cache. These n+1 bits, one bit is indicating whether the block is dirty or not, and the remaining n bits indicating that in what are all the private caches this particular block is present. That is what is called as the presence bits, 1 to n. If let us say block is present only in core 1, then I'm going to set the first bit of the presence bits, and if it is a clean copy, then I'll just set dirty equal to 0. Right? That is what we are going to do here. And all we need to do is, so once you have the state information at the shared cache blocks and the private cache blocks, then we need to run state transition diagrams for these two. And the private cache state transition diagram is whatever we considered previously, the same thing is applicable. But in addition to that, we also need to have state transition diagram for the states associated with this shared cache blocks. That is the shared cache, the blocks present in the shared cache. So I'm going to talk about only the state transition diagram for the blocks which are present in the shared cache. And the state transition diagram for the private caches is same as any of these 4 protocols or 5 protocols we discuss that can be applicable. This is the last slide. So the left hand side, already we discussed the MSI protocol. This is for the private cache. In other words, this is for the private cache state transition diagram is given by the left hand side portion, and the bottom table, the state transition diagram for each of these shared cache blocks, we are going to have this right hand side portion. And here this directory information will be the directory state transition diagram will consist of 3 states, which indicates that whether the block is present in the shared cache. If it is present, whether this block is shared by any of the private caches, or whether this block is in a modified state in any of the private caches. That is what is given by uncached, shared, and modified. Uncached indicates this block is not cached anywhere in the private caches. If it is cached, whether it is in a shared state or a modified state, that is given by shared and modified. So now what happens is, initially the block is brought into LLC. Now there is some core 1 initiated a read request. So core 1 sends a read request to the corresponding home node shared cache. Now in that we are going to check the state of that particular block, and we find that this cache block is not shared in any of the private caches. Now what we are going to do is, so we supply the data from the shared cache to the private cache, and now we'll indicate this core 2 or core 1, whatever is requested the data, is now sharing this particular block. So now we'll be updating the presence bits of that particular core by 1. That is given by sharers equal to P. Initially sharers is empty set. Now P is added to that particular set. So we moved from uncached to shared for a read miss, supplying the data from the shared cache to the private cache. And after that, if the block is in a shared state, let us say now core 2 or core 3, core 4, everyone is requesting the data. Everyone will come to the home node, that means a shared LLC, and everyone is getting the data, and everyone will be added to the sharers list. That is what is given, sharers equal to sharers plus P. Every time when the new sharer comes, we are going to keep adding. In other words, in the presence bits, we are going to set the corresponding bits to 1. That is what is happening in the shared state. There is a self loop for every read request. Now, let us say a block is there in the shared cache, and now core 5 wants to perform a write operation. What it does is, it is going to first send the request to the home node, that means the shared cache, and now shared cache sees that whether anyone is sharing this particular block. Let us say core 1, core 2, core 3 are sharing this particular block. Now this LLC controller is going to send an invalidation signal to core 1, core 2, core 3, because everyone has to invalidate, and only core 5 needs to get the exclusive permission because it's a write operation. So that is what is given by uncached to a modify and a write miss. We supply the data, and the sharers is going to be now core 5 only, irrespective of whether you have the, so in the uncached, in the sense like basically no one else is caching and core 5 is requesting the data, so automatically core 5 is only the sharer. But let us say if you just consider share to modify, there is a write request, core 1, core 2, core 3 are sharing this particular block, and core 5 wants to write it. Now you can see there is a share to modify, there is a write transaction, and we have to invalidate. That means we send the invalidation signal to core 1, core 2, core 3. And after invalidating, we make the core 5 as the only sharer. That is what is given by sharers equal to P, and we supply the data to core 5. And finally, we put the data in a modified state. Because it's a modify, we also going to set the dirty bit to 1. Because in the n+1 bits, the last bit is indicating the dirty, we'll be setting the dirty bit to 1. And now let us say core 5 is having the data in a modified state, but after that core 2 requests the data for a read operation. What is that we are going to do? We supply the data from core 5 because core 5 has the updated data and LLC is not going to have the updated data. Core 5 is going to reply to core 2, and after that the sharers will be core 2 and core 5. That is what is given as sharers equal to sharers plus P, and we change the state from modified to shared, and we make the dirty bit equal to 0 because now both have the data, and the shared cache is also going to have the correct data as it is. So this is what we have to. So when we are considering this directory-based protocols, in addition to the private cache state transition diagrams, we also have to give a state transition diagram for the LLC part. That means the home nodes, distributed LLC chunk. For each of those things, we have to give the state transition diagram. So this is about the cache coherency protocols, and it consisting of basic 3-state MSI protocol all the way up to 5-state protocols, and then we also looked at the update-based protocols, and we also briefly looked at how a cache coherency protocol will look like for a directory-based things and so on. Okay, if you consider any of the protocols, also typically they are working like this. All we need is like we have to represent the entire behavior of the cache coherency using a state transition diagram, and then we have to see whether all the scenarios are taken care by the state transition diagram. And this is important because if the state transition diagram is not properly designed, and if we implement that, and if it leaves out some scenarios, and the data is going to be in incoherent state. So that's it from my side. And if you have any questions, I'll be happy to answer. Okay, if there are no other questions, then.
So would it be possible for you to be there today?
Yeah. So
Four?
yeah, like I was because shifting my office and so on.